Yeah, so thanks for staying back for the last talk. I'm really excited to be here. It has been a very wonderful conference. And since I'm the last talk standing between you and the lunch and probably your weekend plans, I'll try to be efficient. So, but feel free to interrupt. So yeah, today I'll be talking about the kind of work we have been doing on non-Markovian probes of correlated many-body systems. It really stands at the in some sense, the theme of the workshop, I would argue, which is basically this new perspectives in many-body physics, because we're really trying to do many-body physics inspired by tools of quantum optics. So before I start, let me give a thank you to all the people who do the actual heavy lifting, all the postdocs and graduate students and our theory collaborators. The people who are in the bright blue are the people who have directly contributed to this work. And we have also benefited with our collaborations with the theory collaborators at UMass and Brandeis. These are actually not open quantum system theorists, they are field theorists, and I will try to argue how it's actually very beneficial for us to talk to field theorists once in a while, or maybe more regularly. So without further ado, let me explain, let me try to say what are memory effects in quantum systems. They have been alluded to in previous talks. Basically, any open systems whose dynamic depends on its prior evolution or past is called a non-Markovian system. And the standard signature of non-Markovianity is considered information backflow. In this talk, I'll try to convince you why that is not necessarily a good way of thinking about non-Markovianity. But let's just flow with it. The information backflow typically appears as some kind of a time domain recurrence in evolution of system observables, like something which is non-monotonic in time. And there are several measures. There is a small industry of coming up with non-Markovian detection, starting from the work of Breuer and then followed by Rivas, Huelga, Plenio, all these people. The issue with these kind of observations is that usually these kind of small transient behaviors or recurrences appear on a very broad background. So it's like looking at a star in the direction of a sun. It's really a very sensitive measurement. These are usually sometimes appear as transient effects. The timescales are very different from your average decay rates. And as I will try to convince you, these kind of measures or these kind of signatures may be sufficient, but they're not necessary conditions for non-Markovianity. And now one can say, okay, all this is fine, but why should we care? Because there's some experimentalists in the audience. So first of all, if you already non-Markovianity is dangerous in a classical world, please don't try this at home. But in addition, non-Markovianity, if you actually confuse it for Markovian behavior, it can, there was this recent very interesting paper by IBM folks where they showed that if you have non-Markovian errors in your multi-qubit processes, not only they lead to off-resonant coherent errors, which are basic, everyone knows that the coherent errors and leakage errors are the hardest errors to correct for, but they also break the stationarity assumption, which essentially means now if you have a gate sequence, the error budget actually depends on when you do the gate. Usually you should not, like let's say you are doing a randomized benchmarking protocol, and it should not depend on when you do your second, like 2-qubit gate in that protocol. But because of the breakdown of stationarity assumption, there is a genuine problem when you have non-Markovian errors. And in addition, most of the error correction protocols like Shor's code or most of the CSS stabilizer-based codes, they assume temporally and spatially uncorrelated noise. So they usually, most of the error correction codes cannot handle non-Markovian errors. Okay. So let's see how we actually model this. Our favorite way of modeling these things, at least or my favorite way, is to think about trying to write down a master equation. So I'm here showing a hierarchy of master equations, and there's a reason for it. Because when people say we are trying to write a Lindblad master equation by making a Born-Markov secular approximation, actually they do a lump of approximations together. There are actually several approximations which are done on the path of getting there. So let's say the first thing which you have to do is to do a Born approximation. Now, Born approximation basically means that you have I'm always trying to write down some reduced map or dynamical evolution of the reduced system. So it's rho S. I is just interaction frame, it's not super important. And here, instead of, this is my total rho, but I have actually factorized it into a density matrix of the environment and density matrix of the system. This is a Born approximation, and there's also a Born-Oppenheimer flavor to it, because typically you do not consider the environment to be evolving. So you say, oh, there's a separation of timescales, the environment is super fast and the system is slower. So, this is an entanglement breaking approximation, which is automatically true when there is a separation of timescales and the environment kind of does its job and settles in its steady state. Then what we have started calling, at least internally in our group, we do the first Markov approximation, where you actually erase the memory of the system from its state. So the evolutionary memory, this is actually this curly V is the super operator coming from the interaction between system and environment. That is still there, but the equation becomes time local in the state of the system. And then finally, there is a second Markov approximation where you actually consider that the bath is not only fast, it's actually delta correlated, so that you can take the upper limit and put it to infinity. Basically, the point is that there is some kind of a correlator of the bath which you will get from by tracing over the bath and these operators which enter through the interaction, and they are so sharply correlated that if you actually take this integration limit up, the upper limit to infinity, you incur a very small error because for most of the part of that integration, the integrand is 0 anyway. That's the idea. Okay. So now the typical way of thinking about non-Markovianity is this Born-Redfield master equation, which is the second one, which is actually a time local equation in the state, but it knows about the memory of the evolution through the memory of this kernel. So this is how we typically write it. It's basically a second order expansion in the system environment coupling, and you can develop a time domain solution, you can calculate time dependent rates and so on and so forth. And our idea was to try to do better than Born-Redfield. We have to make Born approximation. If you don't allow me Born approximation, I cannot write a master equation. So everyone has to make Born, like if you are committing to a QME, you have to make a Born approximation. But the point is that we can actually, in principle, do not need to erase the memory of the state, because though this is a genuinely time non-local equation in the state, actually this is a well-known theorem in Laplace and Fourier transform theory, that any time non-locality can actually be, is actually a frequency local map. But essentially now, instead of solving for the state physics in time, this looks like a funny object in the first time you look at it, but it's basically a density operators in frequency domain. I can solve for a frequency domain, and as a mathematical operation, I'm totally allowed to do this. So that is what we call the frequency domain master equation, which allows us to include the whole evolutionary memory as well as the memory of the state in the physics of non-Markovianity. And it's actually, as I would say, based on this kind of idea of doing frequency domain analysis of non-Markovianity, it also actually inspired us to come up with a measure of non-Markovianity, which doesn't rely on time domain observables at all. So, and it's worth saying that once you have actually made these approximations, these are irreversible approximations because there's some kind of coarse graining involved here. I think there's a question. Sharply just means it's there is a finite time scale, but it's not 0. Okay. That's all.
So you're stopping there. You're not doing the rest of it.
I'm stopping on the first line.
On the first line.
Yes. In the future slides, I am stopping on the first line. Yeah. So all the results I'll be showing will be calculated using the orange box. Okay. So as I said, this I already alluded to. The way people think about non-Markovianity is basically, this is one of the standard measures of non-Markovianity, which is called BLP after the inventors Breuer, Lane and Pilo. And this is a very simple QTIP simulation. You can, it's just like 5 minutes. You can actually, just a simple qubit coupled to a lossy cavity. If you just see initialize the qubit in its excited state and look for its decay. You see the full numerical simulation is the black dashed line. The Lindblad prediction is the red line, and the Born-Redfield shows you the blue line. And as you can see, this is the idea of this not capturing the recurrences. There are these oscillations in the population at the initial time, and the Lindblad gives you a simple exponential monotonic decay. So basically, BLP-like measures try to pick up these kind of recurrences, and the way they do it is to actually say, okay, you take your system of interest. So we're not talking about system environment, just the system, so state of the qubit, initialize it in some initial state, let it evolve, Now do a second preparation, do the same evolution. So these rho 1t and rho 2t are basically timed evolved density matrix corresponding to two different preparations. And then you take a 1 norm trace distance between these two guys only along those regions where your trace distance is increasing. And on top of it, if you don't think it's complicated enough, you should maximize over all possible initial state preparations. So BLP really takes this to heart that information backflow should appear as a time domain recurrence of some kind of an observable. But as you can see, this is not a directly observable quantity. This is a trace distance tomographic measure, and you are trying to resolve a very short pass transient, so you need high bandwidth tomography to measure this thing. So it may actually do what it sets out to do in a very serious way, but it's not really experimentally accessible in many body systems. So that's what the inspiration was, that we can solve for non-Markovianity in the frequency domain using the full memory. But can we find a signature which persists at long times and also is experimentally accessible to fields like field theory or condensed matter where tomography is not even an option? Okay. So that's what we started. We are looking in the frequency domain. You can use either bond-rate field to actually calculate a two-point correlator and then try to take a Fourier transform of this two-point correlator to get your spectrum. But actually, I'll be using a frequency domain solution. So in the frequency domain, if you have this u of omega, which is what the frequency domain master equation propagator is, it's actually very simple to calculate the spectrum directly. You don't even have to go to the two-point correlator. And here I'm showing exactly the system I introduced on the previous slide, a qubit coupled to a lossy cavity and the spectrum. This is the emission spectrum of the qubit, which is calculated after tracing out the cavity. Using this frequency domain master equation, but you can also use bond rate field, it's not a big deal. And what you can see is, as soon as you use a Lindblad equation, you are supposed to get a simple exponential decay, which should lead to a Lorentzian profile of your spectrum in the frequency domain. But if you do a non-Markovian calculation, this is what you get. There is actually a side peak. This is in the weak coupling regime. The G over kappa is around 1 over 500 here. So this is not some normal mode splitting in that sense. I'll come back to that, what happens in the strong coupling regime. And if you look at the analytical version of the spectrum, it actually looks like a Lorentzian, except that in a Lorentzian, these real and imaginary parts are constants. These themselves are actually Lorentzians. So it's a Lorentzian of Lorentzians, because the real and imaginary parts are themselves Lorentzian functions of frequency. So when we look at this size, so there are two peaks. The center peak is actually what corresponds to the Markovian limit. And by looking at the gamma effective, which is the width of the peak and its position, you can calculate the lamp shift and the decay rate, which your Lindblad would predict. However, what is this side peak? This side peak, amazingly, actually is nothing but the Fourier transform of the Green's function of the cavity, which is the engineered bath to the qubit. So actually, this is the imprint of the environment on the system spectrum, which actually makes sense, because in non-Markovianity, the environment and system can actually share some coherence. And so it's not entirely surprising that it's almost as if we are looking at the environment, but through the lens of the system. And that's why in the emission spectrum of the qubit, you are actually seeing signatures of the cavity emission, which is what this peak is. And in fact, its width is also kappa, which is it should be gamma b, the cavity line width, and so on and so forth. So based on this, these two very evidently different looking spectra, we actually came up with a non-Markovianity measure, which essentially tells, which is based on this, which we call the spectral measure of non-Markovianity, which is nothing but inspired from the information theory perspective, that when you have two probability distributions, and if you confuse one probability distribution with another, let's say you have a P of X and a Q of X, the information cost which you pay is what is called relative entropy or Kullback-Leibler divergence. So if you think about it, the spectrum is nothing but a probability distribution in frequency domain. So of course, I have normalized the spectrum so that it should make you comfortable. The total area is 1. But the idea is the spectrum tells you how much are you emitting, what is the probability of emitting at a given frequency, what's the amplitude. So in some sense, this is nothing but the kind of the information cost of making the Markov approximation with a per unit bandwidth. And this per unit bandwidth is just to resolve and privilege the features on small frequency scales and not necessarily in the wings of making the Markov approximation. So if I basically have a probability distribution which is in the solid black and I confuse it with a probability distribution which is the dashed black, how much information will I lose? This is that non-Markovianity measure. So it, as you can see, it relies solely on observable quantities. It's non-tomographic. And it actually, our viewpoint of understanding non-Markovianity is not a positive signature like information backflow. What we are saying is deviation from Markovianity is non-Markovianity. Anything which is not Markovian is non-Markovian. It's almost tautologically true, right? So we actually go ahead and we calculate this measure for a system coupled to a thermal environment. And you can see maybe in this waterfall plot, you can see this, that as we are actually increasing the detuning between the system and the environment, the non-Markovianity is increasing. And as the environment bandwidth is increasing, the non-Markovianity is decreasing. Which actually makes a lot of sense if you think about it. Because when the system environment are at resonance, there is genuinely no time for the environment or to retain any coherence which it is receiving from the system. So in fact, we actually find that for large detuning between the system and environment, the non-Markovianity actually grows logarithmically with the detuning, and it actually decreases. This actually makes sense because as you are increasing the line width of the bath, you are becoming more and more wide in frequency, so you are getting more and more delta correlated in time, so it's not surprising that the non-Markovianity should decrease. And the nice thing about this is the frequency domain calculations is everything is analytically extractable, so you can actually get this power quadratic, and that's a -2. And now one very interesting thing which we found, and this is my beginning of talking about correlated baths, is that, well, what's the simplest kind of correlated bath I can have? Gaussian correlations. How do I get Gaussian correlations? By putting squeezing in a cavity. So this is a qubit coupled to a squeezed cavity. And you can see, interestingly, when the squeezing is 0, I see some kind of non-Markovianity. And then I start increasing the squeezing strength, which means I start increasing the correlation strength in the cavity. Interestingly, at some special value of squeezing strength, which is shown in this blue spectrum, the system looks Markovian. So this idea that more correlations mean non-Markovianity or less correlations in environment means non-Markovianity, the situation is actually more subtle than that because it can be actually non-monotonic. In fact, here what is happening is that, as you know, or at least the people who work with squeezed cavities know in quantum nonlinear optics, that in the Bogoliubov basis, the effective frequency of the cavity becomes the correlation dependent. So in some sense, this is a squeezing induced resonance between system and the environment. And that's where you see minimum non-Markovianity. So, and of course, I won't cover this in the interest of time, but we also find that unlike the Born-Redfield quantum master equation, if we actually model the dynamics of this system using the frequency domain master equation, it actually preserves positivity for all times. I'm not claiming frequency domain will preserve positivity in all cases, but in all the empirical, but this actually shows or indicates that it's not just the entanglement breaking or the Born approximation, which is of course the primary culprit of breaking positivity in your open system descriptions. This shows that even memory effects can contribute to positivity breaking. Because in both cases, we have made Born approximation. The only difference is that in the frequency domain, we do not erase the memory of the system, the state of the system. Okay, and then this is actually to just motivate further why we think that this is actually a better way of thinking about the non-Markovian instead of information backflow. This is just plotting the BLP measure as a function of detuning for the thermal case and the spectral measure. And what we find is, of course, there is a certain region where BLP strictly remains 0. So these are the times. This is the regime when the lamp shift and the decay of the system are heavily time dependent, but they remain positive. And that BLP infers as Markovian. because it really takes this idea of negative rates very seriously, because that is a necessary condition for information backflow, and that's why it misses to detect any kind of non-Markovianity. So one can say, okay, yeah, but these guys had a philosophy and they were following it. But in my next exact problem, there's actually a problem with that philosophy, which is much more fundamental. And here, BLP actually gives you a false positive. What we did was we actually just calculate, like literally a simulation of a qubit coupled to a Markovian squeeze bath with constant rates at all times, right? Just a normal, regular simulation. And what BLP actually predicts is a finite, non-zero non-Markovianity for a Lindblad evolution of a system coupled to a squeeze path. And I must add that at the level of two-level systems, all time domain recurrence measures have been shown to be equivalent. So what BLP has this problem, all will have this problem. Like you can choose your favorite measure, RHP, information bay. What is actually happening is that there are actually oscillations due to the competition of squeezing and free evolution of the cavity, which appear as oscillations on the trajectory of the state. These are not observable oscillations. And BLP misdiagnoses them as actually evolution, oscillations due to backflow from the environment. There is no backflow possible. This is a genuine Lindblad equation. So because of that, I would argue that spectral measures are at least based on our studies, are probably a better way of thinking about non-Markovian. At least we shouldn't get too attached to this idea of information backflow. In the interest of time, I'll skip this slide. But yeah, please remember the question and someone can ask that and I can answer you why I think spectral is better than time. Okay, so now actually talking about many-body correlated systems, the inspiration came from our field theorist friends. They were like, yeah, good, you guys are not thinking about tomography, so now we are talking. So how do we go from here? So basically, this is a typical system to think about it. Like, let's say that you have two interacting Klein-Gordon massive fields in 3+1 dimensions, and the only difference, so phi is my system field and chi is my environment field. And there are two potential cases. One is a linear interaction, n is equal to 1, and another is a nonlinear interaction. This double dots is just time ordering, which is important. And now in space-time, these looks very, every field theory is very complicated. But as you can see, a Klein-Gordon field is nothing but a collection of oscillators in the momentum space. So I'm writing this in the momentum space. And their point was to try to average out, trace out all the orange guys and try to write down the equation for the blue. So the question is, which one do you think will be more Markovian? Which case, n equal to 1 or n equal to 2? That was the question. No, you can, very good. See, yeah, that's the point. That's the beauty of talking to an intelligent audience. Yes, n equal to 2 is a better, is a more Markovian, and the very simple way of thinking about this is that genuinely there is a notion of a multi-mode bath, because you actually have a free variable p which you actually can integrate out. And but more evidently, where this is actually the environment correlation function as presented to the system. So let me be clear. The environment is always the same, the HB, but HSE is different because of n is equal to 2. So the environment correlation spectrum presented to the system is different. So this for n equal to 1, as you can see, it always keeps oscillating, but for n equal to 2, it looks very peaky and Dirac delta-like. And that is the point that Markovianity is a very special limit which appears in the reduced systems, which is entirely determined, and this is a bold claim, entirely determined by the environmental correlation functions as seen by the system. Okay. So we really wanted to test this idea and apply it to genuine many-body physics. So what is the most extreme case of correlated environments I could think of? Well, a quantum critical point. This is as correlated as you can get. And we wanted, we started in 1D because we wanted things to be still solvable. So this is everybody's favorite transverse field Ising model. And as you can see, this is the phase diagram. Lambda is the ratio of the transverse field to Ising coupling. And there's a symmetric paramagnetic phase. and a symmetry broken ferromagnetic phase, and this phase transition is continuous, which happens at 0 temperature. And then there's this gray region which is called quantum critical region, where people have seen people see anomalous scaling because of the interplay of thermal fluctuations with these long range correlations. Okay, so this is very well known. And what we did was, okay, sure, this is something which yes, thank you. This is something which I learned quite late in my life, which I'll tell you later in the question answer session. But there's a lot of advantage, even from the point of view of doing critical, like RG, to go to Jordan-Wigner transfer, to go to this kind of frame where you can model these as free fermions using Jordan-Wigner transformation. In this picture, this is actually just completely quadratic, the Hamiltonian. It's diagonalizable. You can write all these energies. And as you can see, the quantum critical point appears, or the phase transition appears at lambda c equal to 1, where the theory becomes conformal, because k equal to 0 mode is 0 energy. So we said, okay, fine, and then let's try to make a open system out of this. But I don't want to measure this complicated system. I love measuring qubits because they're very simple. When I say experimentalists love measuring qubits. So let's couple a probe qubit to this system, and I'm taking a kind of a central spin model. So the qubit is coupled with equal strength to all Ising spins. And in the Majorana basis, it actually looks like this nonlinear interaction. And this nonlinear interaction actually looks innocent, even in the limit of weak G, it's not very accessible, this system, the whole system, with the DMRG methods. So you can't just simulate the system for many lattice sites very easily in the presence of these kind of terms. At least we have tried, and it's not so easy. It's not impossible, it's not simple. Okay, so then what we did was, okay, but we don't want to think about the orange system. We would actually want to trace it out. And that's what we did, and come up with an effective equation for the probe qubit. And our hope is that what the Ising system is doing, including its phase diagram, will somehow map on the dynamics of the probe qubit, because this we can measure. And we actually are able to do this. Let's see, so when the system goes critical, the Ising system goes in critical, the environment, what we find is that we actually, the rates become constant or completely Markovian. So we get Markovian physics at the quantum critical point. And if we initialize the qubit in its equatorial state, it completely dephases and the coherence goes to 0. However, away from criticality, which means if the Ising system is away from its critical point, what we find are all these rates as I'm moving away from lambda equal to 1, I'm getting more and more away from criticality. The rates start changing in time. So this is the sign of non-Markovianity. You can even see some of them can become negative, and eventually they become 0. And what that manifests as is if I initialize the qubit in its equatorial state, it actually retains its coherence, and there's a fractional decay of coherence. And in fact, depending on how far away you are from from the critical point, the more fractional decay or the preservation of coherence you will see. So in that was in the beginning, it looks like it's a no-go or a non-starter, because I'm trying to write down a quantum master equation near a critical point where the qubit is 0 frequency in the interaction frame, because this is a dephasing process, and the gap has closed. So what is the perturbation theory parameter delta? So it looks like it's a non-starter, but actually, as you can see, we actually benchmarked our results against exact results for this model, which have been obtained using Loschmidt echo, because in this case the system environment and the system Hamiltonian commute, so an exact calculation is possible, and we get not only quantitative agreement but not only qualitative agreement but quantitative agreement with the exact result. So we really believe that the QME is working, because the relevant perturbation parameter is not G over energy scale but G over bandwidth, and that's set by the Ising. So finally, we can also do the spectral diagnostic of the quantum critical point, like I said, which is the n sub s. And so for that, we actually first plot the spectrum. As I said, at criticality, you get almost Lorentzian with this rounding, and this rounding is because we are doing statistical field theory, so the UV cutoff is finite. This is just the band edge, which is set by 4 lambda j at criticality. And if I really take the continuum limit, which is the field theory limit, then I get a perfect Lorentzian, because then the UV cutoff is infinite. And if we go away from criticality, in fact, the Ising gap appears as a gap in the qubit spectrum. This is the qubit emission spectrum. So actually, of course, if there is a gap in the spectrum, that also manifests in the probe qubit spectrum. And in fact, there is this large Dirac delta peak-like structure at zero frequency. That's just showing that you actually have some trapped steady state coherence because of the fractional decay, because it never goes away. This qubit always has some coherence left at its own frequency. And when we can finally try to do the spectral measure as a function of lambda, this is the plot where you can see that as we are going, again, this is just for different values of j, just to show that as we are going closer to the field theory limit, when j corresponds to almost infinity, with a goes to 0, you are getting basically 0 ns, which means 0 non-Markovianity at the critical point, and as you move away, you add the non-Markovianity increases. And then we can actually do really phase transition physics of this ns, take a derivative, and we see a very sharp discontinuity. Now, if you remember, the ns was like a relative entropy, and this is the first derivative of the entropy, which is discontinuous, which is indicative of a second order phase transition. So, of course, the interpretation is that this is a non-equilibrium entropy, which is playing the role analogous to thermodynamic entropy. So, in that sense, we can actually map out the full phase diagram of this Ising system by just looking at the probe qubit dynamics and its non-Markovianity. And I think I'm completely out of time, but I can just, this is very quickly, we can not only map the whole phase diagram, including in the quantum critical regime, we can even map the RG flow by just looking at the rates of the system along with their velocities. So I don't have time for this, but sorry. So just to conclude, I hope that I have given you at least a brief overview of why spectral probing of non-Markovianity can be a powerful diagnostic in not only few body systems, but even many body systems. And these is extensive. There are several opportunities. In fact, there is this tantalizing paper which was came out, I think, last year, where everything is a quantumizing model, because you just need sufficient complexity in your long rangeness in your Ising model, and you can even do symmetry protected topological phases. So now we are just scratching the surface. The point is that if we can actually just have very simple probes attached to these kind of systems, and we can map their entire phase diagram by just looking at the dynamics, it would be an interesting way of thinking about these many body systems. Thanks.
So thank you for the talk. I already see a question.
Thanks, that was super cool. So first question, in the cavity QD example that you gave,
yes.
There was a single mode cavity. Have you also considered multi-mode?
Very good question.
And does this Green's function interpretation still apply?
Yeah, so very good question. So yes, we just use single mode in the sense because from an engineered reservoir perspective kind of idea. But yes, we have applied, actually, we have learned from your paper and done waveguide QED, applied this to waveguide QED systems, and indeed that is true that you still get the imprint of the photonic spectrum of this multi-mode physics on the qubit. That is still correct.
And so also, because in the system you have two different origins, one is strong coupling and the other is that you have a structured reservoir.
So we deliberately kept the weak coupling very weak, so that we, actually that's a good question. So what, as I mentioned, this peak appears just because we are doing a non-Markovian calculation, and that is a more exact calculation. If you actually keep increasing your G, what would happen is that this is actually the peak which on resonance becomes the normal mode splitting.
I see.
So this is actually the remnant of the normal mode split peak in weak coupling regime, which you will miss if you don't do a non-Markovian.
So there's sort of an equivalence between these two origins of non-Markovian.
But the problem is Lindblad says there is a single mode spectrum, like a single peak spectrum in weak coupling regime. And what I'm saying is that's not true, obviously.
And if I can sneak in one more. So in your in the latter part, if can you use your probe qubit as also a control qubit to control the phases of your chain?
Well, then I would not weakly couple it.
Yes.
Because I'm trying to then control, but because it's a, are you thinking of something like quantum physics or something, like a single impurity physics of sorts? Because we are trying to basically flip the problem, that we are trying to actually measure something which is very weak, very easy to measure, by coupling it weakly to something which is, and the interesting thing is, as I said, that's why we benchmark this calculation against Loschmidt-Echo problem, because Loschmidt-Echo doesn't assume weak coupling. It's an exact calculation when things are commuting. It still works. Now, how you can use this single impurity to affect the behavior of everything, I think then it's a different regime. Then I think we are talking about localization physics, which I think is possible. And we have explored it in at least like the spin boson systems, not in this particular one.
Okay, cool. Thanks.
I had a question or comment regarding the first part of your talk, where you have a finite bandwidth bars and a qubit coupled to it. So when you see this additional peak appear,
Yes.
We had something very similar in our experiments.
Okay.
But our interpretation, I don't know if this is the same as yours, is that when you couple more strongly, you basically start to couple to the band edges, and you're coupling to the bound states that exist at the bands. And so the stronger you couple, you couple, the more you couple to those bound states. And this is actually an oscillation that is not radiative anymore, but which persists. So you have a combination of an exponential decay with the oscillations, but there is a little bit of oscillation that just persists, and that's the beating between these non-decaying bound states. So I was wondering if you see this. I mean, in your dynamics, I saw that the oscillation kind of dies off with time, but if you increase your coupling even more, would you see anything that survives?
So that's a good question. So there are several features which tell us that this is actually the Green's function or the emission spectrum of the bath, because you can be, okay, at least as a theorist, I can actually change the width of the correlation function of the width of the bath. I can actually change its frequency, and the width and the peak of the position of this peak actually scales linearly with the bath physics. Now, what you are saying, this is also possible, that you can actually, if you actually have a coupling, you can couple very strongly to bound states, but for that you need a band edge. And that actually happens in Ising. If we deliberately couple our qubit to the band edge in the finite UV cutoff theory, then we can see some oscillations, but those oscillations are not, so let me actually say this. This is probably the easier way of thinking about this. Let me go to so what I'm trying to get at is that there are these additional, this is what also leads to non-Markovianity. This is the band edge effect which you are referring to. And the peak part which I am referring to is before the band edge. This can happen even when you are in the band, but there is some kind of a non-Markovian coherence between the system and the bar. But you are absolutely right that just because of this band edge, we get a finite non-Markovianity. That's absolutely possible. Yes.
So, is it correct to say that this measure requires time that the spectral function is time translational invariant? Because I know that, for instance, you can have a non-Markovian effect in time local Lindblad with negative coefficients, and there you have time dependence.
So I would argue that
this... So you cannot go to a spectral, to the omega.
So I would argue that the presence of negative rates, even at a level of Lindblad, is not the indication of non-Markovianity at all. Because and it sounds like a controversial statement, it's not. And the reason for that is the Lindblad can have several rates, right? Like a heating and a cooling and everything. And when you write down the equation of motion of your observables, you can have difference of these rates which are appearing, which set the decay rate of your observable. So it's actually the net or the net rate, the sign of the net rate, which should be looked at when we are deciding Markovianity or non-Markovianity. By itself, different dissipators having plus or minus or complex rates is not good enough to actually detect anything or say anything about non-Markovianity. And we have seen this. We have actually found that we can actually write Lindblad equations where you can have different dissipators which have positive and negative rates, but the total rate of the observable remains positive at all times.
No, but these are positive and negative in time.
Oh, yeah, okay. But if you have positive and negative in time, as I said, that's definitely a necessary condition, but I don't think it requires time translation and invariance, at least to get the spectral measure. I don't see why that should be the case. We can talk more about it if you're interested.
Hi.
Yes.
Talk was very nice, thank you. So I have a trivial question and perhaps another one non-trivial. So you were showing at the beginning, if I remember right, that you have a benchmark. In the trivial case, when you have one spin and one boson, you solve the problem exactly, you compare it with your method, right?
Yes.
All right. So I presume you cannot solve many body situations, right? So you cannot solve the case in which the system
we can solve this many body situation exactly.
No. The path is many body, but your system can be many body.
Oh, yeah, very good question. So, yes.
This is the trivial question.
Well, it's not it's a good question. Depends on how many body is many body. But basically what we are trying to do is to actually flip the point of view. We are deliberately trying to keep the probe extremely simple. So no matter what is your many body system, it can be a Heisenberg XY model, it can be Ising model, but the probe is at most 1 or 2 qubits. So I can measure the spectrum exactly.
No, right, because your point is, I appreciate your point. Your point is a probe of non-Markovianity, not giving a method to solve a
But in principle, as you said, we have actually tried to deploy our spectral measure directly on the Ising also. But that has to be done numerically, in the sense that we have to calculate the spectrum numerically. Or at least I cannot show you a closed form nice expression. For these kind of systems, we have an analytical handle on all these rates.
Okay. And now something that is bothering me, but maybe I'm very tired. So it was a long and beautiful conference. So when you couple the qubit to the Ising model, right, you also bring the Ising model to criticality, isn't it? You show results in which the band is critical.
Yes.
But your only approximation is Born. It means that the coupling is small between the system and environment.
For the solid lines, yes. For the dashed black lines, no.
Okay, so you are never in a situation in which you have perturbative coupling and critical environment, because this would worry me, right? To do perturbation theory.
Yeah, so this was our primary concern, that in 1D Ising, all perturbations are relevant. Anything which you couple will take you away from criticality, correct? That is the whole point of 1D. And that's why we actually benchmark using an exact calculation, which is the dash black. So amazingly, that was the point, that you would think that how can G be small if it's a relevant perturbation?
Yes.
But the relevant perturbation parameter is not G over the gap from the criticality. It's G over J, the Ising, because that sets the bandwidth of your bath. So in some sense, it's the Caldera-Leggett understanding, that when do you see that you are weakly coupled? Because why is Caldera-Leggett always leads to kind of non-Markovian, Markovian Lindblad equations is the go-to model, because it's a very broadband bath. Mm-hmm. So no matter how much G you have, it never overcomes the bandwidth of the bath.
Oh, very nice. We're to talk more. Very nice. Thank
you. Sorry. Yeah.
Thanks a lot. This last part is really cool. Can you give some sense of scale? Where is your qubit frequency living? Is it above the UV cutoff of the system?
No. We can actually tune the qubit frequency, but actually in this case, it doesn't matter, because this is a dephasing process. So it's pure dephasing, but we are actually, that's a very good question actually. We are also trying to do transverse interactions where you can actually park the qubit either in the band, near the band edge, or in the gap away from criticality, and then see how your rates actually flow as a function of your qubit frequency. What happens is, and this is something which I did not have time to discuss, that when your probe itself is quantum, so I'm saying why I'm saying this is also a qubit, but it's almost classical for our purposes, because here the system environment interaction commutes with the system Hamiltonian. It's a pure dephasing process, and qubit is also sigma z. But when you have a sigma x in the interaction and sigma z, now the fluctuations of the probe also matter. And there, but I think the nice thing about Spectrum is it actually encodes all that information. So it is possible to actually, in that case, actually just after deconvolving the probe, the effect of the fluctuations of the probe, you can again make the same phase diagram and say, oh, I'm in the band gap, I'm in the band edge. So you can just tune your qubit frequency and map the dispersion.
But for now, we speak of just pure dephasing.
Right now, I'm just talking about pure dephasing because it's simple. That's why. But in principle, you don't have to confine yourself to pure dephasing.
So I think with this, we finish the session. We thank all the speakers for their fantastic talk of this morning. And, so you clap hands, but then we... Since I am the chair of the last session, I would like to express, I think in the name of everybody, our sincere gratitude to the organizers for this fantastic conference. We really enjoyed it. And I'm very envious that I will not be part of the program, because after such a great start, I don't know what else can come. So I will try to follow you. So thank you.
Yes, so yeah, now it's true what you say. Now we have to keep up the level for the program for those of us who stay. But just, I wanted to say just thank you for coming. I think that the level of the talks and the discussion has been excellent. So I really think that it has been a wonderful conference. And yeah, so thank you.